we're now going to work a little bit more with the binomial distribution. And to do this, I'm going to go back to the original example that I gave, where there's a 3% chance of catching the disease. And there's 50 people who are exposed to the disease. Okay, and then we're going to let x equal the number of people who catch the disease. Okay, and as we found out last time, the number of trials, n, was equal to 50. In this case, the success was catching the disease, because x is the number of people who catch the disease, and there's a 3% chance of that happening. And so the failure is not catching the disease, and there's a 97% chance of that happening. Okay, so now what I want to do at this point is I want to really emphasize the fact that x is a random variable, and as such, you could make a table with the possible values for x. And they would go from 0, because you could have nobody catching the disease, or 1, 2, 3, 4, 5, and this would go on up to 49 and 50. So you'd have the numbers 0 through 50. So any binomial distribution has a corresponding probability distribution where the x values go from 0 to the total number of trials, because you could have no successes all the way up to every one is a success. Okay, and the binomial probability formula that we learned actually gives you the probabilities in this table. So like, for example, we found the probability that x is equal to 2. And so this was 50, choose 2. The probability of a success raised to 2 successes. The probability of a failure raised to the number of failures. And when we plug this in, we got that probability. So 50 choose 2 times 0.03 raised to the second times 0.97 raised to the 48th. And this gives me 0.2555 if I round to 4 decimal places. Okay, so now the important thing to realize is what this binomial probability formula gives you is each of these probabilities. So this one is 0.2555. Okay, so this is the probability that it's equal to exactly 2. And I'm going to write them vertically like that, so I'm not trying to squeeze them in here. So that's the probability that it's exactly 2. Okay, but let's say I want to find the probability, let's say that x is less than or equal to 2. That no more than 2 people catch the disease. And more likely, that's what we're interested in. Not that exactly 2 people catch the disease, but we might want to know, what's the probability that there's not going to be any more than 2 catch the disease. Okay? Now, this amounts to adding the probability that 0 catch the disease, 1 catch the disease, and 2 catch the disease. So you could write it like this: x equals 0 plus x equals 1 plus x equals 2. That's what it would That's what you would have to do. You'd have to find each of these, and then you'd have to add all three together to get the probability that it's less than or equal to 2. There's no shortcut formula. Okay, so what I would do, you don't have to write this out every time. I would take your calculator and just go back. I have the thing for 2 in there. So I could go back and I could say 50, choose 0, 0.03 to the 0, and then 0.97 to the 50th. So you have to change those 3 things. You have to change this, this, and that. And then I could hit equals. And this would be the probability that nobody catches the disease. So 0.2181 if I round to 4 decimal places. And then I would write it in the table. Okay, now I'll do 50, choose 1, 0.03 to the first, and then 0.97 to the 49th. If you can see that. And so then hit equals, and I get the probability for that. So this is 0.3372. Okay, and so there you go. I got each probability. So now I can add all 3 of those. 2181 plus 0.3372 plus 0.2555. Okay, and I get and it looks like it's 0.8108. And there you go. That is how you would do one like this, an inequality. Okay? So now let me show you something here. That 0, 1, and 2 is already like 81% of the probability, right? You got the majority right here. And then you're going to probably have a lot for 3 and maybe a little bit for 4. And by the time you get to these numbers up here, to 4 decimal places, they're all going to be 0.0. It'll be something like, 10 up here would be like 0.0000000 something. Really, really small. They wouldn't even show up on this table. So a lot of the probability is going to go on down at this end. And the reason is the probability of a success is so small that you are much, much more likely to have very few successes than to have a whole bunch of successes. And these are very, very unlikely. Okay? So now, the other thing is that if you add up all of these probabilities, they add up to 1. And that can be very, very useful. So let me give you an example. Let's say I want to find the probability that x is greater than or equal to 4. Okay? So what I want to find is that the probability of 4, 5, like 4, 5, on up to 50, right? I want to find all of these and then add them up. Now that would take forever, and most of these are going to be very, very small. And so what I'm going to do is I'm going to use the fact that all of them added up equals 1, right? When you add them all up, it equals 1. And so what I'm going to do is I'm going to circle the ones that I want, all of these. Okay, I want all of those, and then to get this probability, I'm going to take 1 minus the remaining ones that are not circled, right? So it looks like I got to find the probability for 3 there. And then I'm going to add all these up and subtract those from 1. If I want all these, then I take 1 minus the ones that aren't circled because they all add up to 1. Okay? So I'm going to do 50, choose 50, choose 3 times 0.03 to the third power times 0.97 to the 47th power. And you can see that that looks like it's 0.1264. Okay, so now I'm going to add all of these up right there. And so I've already added these three, and I got 0.8108. So I'm going to do 0.8108, and those are these three. And then I need to add the 0.1264. When I add all those up, I get this. I get 0.9372. So I'm going to take, to get the greater than or equal to 4, I take 1 minus this. So 1 minus the answer, and I get 0.0628. And so what that means is 4, 5, 6, 7, on up to 50 is only 6% of the probability, 6.28% of the probability. Okay? So what I'm doing is I'm using the complement rule is what I'm doing here. Or you can think of it as all the probabilities add up to 1. So if what you want to find is like this huge part of the table, well, you don't find all of those. Find the number that you don't want in here and subtract that from 1. Okay? So notice when I'm finding the probability that it's greater than or equal to 4, I'm not even including 4 in my count, because what I'm including are the ones I don't want, and I'm subtracting that from 1 to get the ones that I do want. Okay, so now let's try another example, and then I'm going to give you a couple to do. Okay, so this was 3%, which is a very small probability of a success. And so all the probability was on the lower end of the table, and these are all really, really small probabilities. So now let's do the reverse, where we have a high probability of a success. Okay, so in this one, let's just say, we'll say 89% of adults, and I don't know if this is true, I'm making it up, but we'll say 89% of adults have a credit card. We'll say, okay? And now, let's say a sample of 20 adults is selected, and we can let X equal number of adults that have credit cards. Okay, so for example, I might ask, what is the probability that exactly 18 have credit cards? Okay, so this is exactly 18. So I want to find the probability that X is equal to 18. Okay, and I guess I need to get N, P, and Q. So N in this case is 20. 20 adults are selected. Each one's a trial. Either they have a credit card or they don't. So N is 20. The success here is that they have a credit card, and it looks like the probability of that is 0.89. So the failure would be they don't have a credit card, which is 0.11. So if I want exactly 18, then I'm going to do out of 20, choose 18 successes, 0.89 to the 18th, 0.11 to the second. Okay, if I want 18 successes, then I want 2 failures. And that'll give me the probability of exactly 18. Okay, so 20, choose 18 times 0.89 to the 18th, times 0.11 to the second. And it looks like what I get here is 0.2822 if I round to 4 decimal places. And so what I have here is I have the probability for 18. So you can think of this as a random variable with the probability distribution. Okay? And this probability distribution is going to go from 0 to 20. But now all the probabilities are going to be up at the upper end, the right end, up here. Because the probability of getting a success is high. So you'd expect to have a lot more successes up here. So what I'll do is maybe I'll do 0, 1, 2, on up to, I'll say 14, 15, 16, 16, 17, 18, 19, 20. Okay, and how do I know to start at 14? Well, I just know that because of the question I'm going to ask here. So you'll have to decide, kind of how to make this table, and you can look ahead to what questions they ask you to know kind of what to include here. Okay? But let me write this probability right here, because that's what that is. 2822. So that's the probability for 18. Okay? So now what I could do here is I might ask what's the probability? So B here is what is the probability that X is greater than or equal to 17? Okay, well what that means is I need 17, 19, 20, and then I have to add all 4 of those up. So what I'm going to do is I'm going to move this like this, take my calculator, and I'm just going to go back and edit these and then write them down. So I'm going to do 20, choose 17.89 to the 17.11 to the third. And then I get that 17 is 0.2093 if I round to 3 decimal places. And now I'm going to do it for 19. So 20, choose 19.89 to the 19, and then 0.11 to the first. And then I get 0.2403. And now I'm going to do, 20, choose 20. 0.89 raised to the 20th, 0.11 raised to the 0. And this is 0.0972. Okay, and so those are the 4 that I need. So this is just going to equal 0.2093 plus 0.2822 plus 0.2403 plus 0.0972. Looks like when I add all that up, I get 0.8290. So that would be the probability that it's greater than or equal to 17. Okay? And now let me ask one more. We're going to ask, what's the probability that X is less than, and in this case, I'll say strictly less than 15. Not less than or equal to, but strictly less than. So I want 0, 1, 2, on up to 14, right? And so what I'm going to do is I'm going to circle the ones that I want, and now I need to take 1 minus the ones I don't want. So what I need to do is get 15 and 16, add those in with the ones I already have, and subtract those from 1. Okay? So now let's do 15 and 16. So 20, choose 15 times 0.89 to the 15th times 0.11 to the 5th. And that is 0.0435 if I round to 4 decimal places. And now 16. So now I do 20, choose 16, 0.89 to the 16th, and 0.11 to the 4th. And I got, for this one, 0.1099. Okay, so I want 0 through 14. So I'm going to subtract all of these from 1. I'm going to take 1 minus all the ones I don't want. 1 minus. So now these 4 are 0.829. 8290. I'm going to add to that 0.0435 and 0.1099. And then that's adding all of these together. And when I do that, I get 0.9824. So this is 0.9824. I'm going to take 1 minus the answer, and I get 0.0176. And this is the probability that it's less than or equal to 14. So all of these has that probability. Okay, so that's another example. This time, since there's a high probability of a success, all the action is happening down at this end. Okay, so there's a lot of work involved here, but you can see it's reasonable when you learn kind of the system that I'm showing you by just editing and placing them in the table and then adding, subtracting what you need using the complement rule. This is doable. It's not the easiest thing, but it's not like overly difficult. It's not unreasonable. You can do this. So, in fact, in the next couple videos, I'm going to give you a chance to do this.